I'm Anil Kumar sharing with you concept of inverse functions with three excellent examples. The question here is, find the inverse of functions graphically and algebraically, state domain and range for both. So there are two parts to this. First, we have to find inverse of a function, and that too in two different ways, graphically and algebraically. And in part B, we have to find domain and range for both. We'll consider three functions. First is a linear function, f of x equals to minus half x plus 1, where x is between minus 2 and 4. The second one is a quadratic function, f of x equals to 2x squared minus 4x minus 1. And the third is square root function, square root of minus 2x plus 6 minus 1. Things to remember, when you do graphically, then what should you do? Let me summarize. So if you have to draw a graph, in that case you could reflect f of x on y equals to x to get the inverse function, right? So that is the first way how you should get graphical solution. Second, algebraically the steps involved should be, let's write algebraically here. You should swap x and y and then solve for y. Now, as far as the domain and range are concerned, you should remember that domain of the function becomes range of inverse function and range of function becomes domain of inverse function, right? Now, you should also note that inverse may not be a function, right? So that is also possible. So when you do these three examples, you'll actually review all these concepts which you have learned about inverse functions. So now I would like you to pause the video, copy these questions, solve, and then look into my solutions. The very first function which we have taken is a linear function. We need to find inverse of f of x equals to minus half x plus 1, but there is a constraint here. Make a note of this. Now that also gives you domain, right? So the domain of, as far as the function is concerned, the domain is between minus 2 and 4, both included, right? That's what it means. Now graphically, let's first sketch the line minus half x plus 1. We could start with the y-intercept of 1, which is, let's say, here. And then slope is negative 1 over 2. Means go down 1 and 2 to the right, right? Well, we have reached our constraint in the next step, which is at 4. Go down 1 to right, right? So that is the position which is for x equals to 4. You could also go up and left, right, too. So go up and left too. So that is at minus 2. So what you see here is a line which points as shown. So if I connect it, I get my function, which is a line segment. Since our domain is restricted between minus 2 and 4, we'll just show this particular segment, right? To get the inverse graphically, we need to reflect this on a line which is y equals to x. So y equals to x is a line which is being drawn here. The graph is not very clear, but I hope you can make the sense out of it. Now that is the line which is y equals to x. So we'll reflect each point on this line, right? So let's begin with the extreme point, which is at 4 minus 1. So this point, which is 4 minus 1, it will become minus 1, 4, right? So it will become minus 1, 1, 2, 3, 4. So that is the reflection. Now, graphically, you could also show it like this. You have to go diagonally, right? You have to go diagonally from here. So you go 1, 2 and a half, half, 1 and 2. Do you see that? So you reach that point. Perfect. Similarly, we can go to the next point, 1, 2. So that's the next point. Now here we have to go kind of this way. So we get this point here. And this is at minus 2, 2, which will become 2 minus 2. So 2 minus 2 will be right there. So the line which you get as a reflection on y equals to x can now be drawn as this line. Okay. So this is your f inverse. Inverse is a function in this case since the line passes horizontal test, right? Okay. So graphically we have already shown the inverse of the function. Now let's do algebraically. So graphically, let me write down, reflect the line in this case on y equals to x. Okay. Algebraically, we need to swap x and y. So we could write the equation as y equals to minus half x plus 1. First step is interchange x and y, right? So we get minus half y plus 1. Then we need to isolate y. So we can get x minus 1 equals to minus half y. Multiply by minus 2. So get minus 2 times x minus 1 equals to y. Or we can say y is equal to minus 2x plus 1. So that is the inverse function, right? Minus 2x plus 1. You can see that the y-intercept is 1 and the slope is 2, negative. So that works. So algebraically, that is your inverse, which is correctly represented by the line which we have already shown. Correct? Now let me write domain and range for the function. So let's say d of x is given to us between minus 2 to 4. Now let's calculate the range. Now if you substitute minus 2, which we did, we got the value of 2, right? So at minus 2, if I write minus 2 here, in that case that becomes, this is 2, sorry. So in that case this point here is at 2 and it goes down to minus 1, and therefore the range is from minus 1 to 2. So that is the range and domain for f of x. Now as far as the domain range for the inverse is concerned, let's write in a different thing, f of inverse x. The domain now becomes the range, I mean that part, will be x greater than equal to minus 1 and less than equal to 2, and the range will be this part, which is minus 2 for y, right? as you can see. Okay, so what you also notice is that the domain and range swap. So this is very important to understand. So I hope with this simple example you have understood clearly that to graph an inverse function you have to reflect it on the line y equals to x. Their domain and range interchange, and for algebraic solution you need to really swap x and y and then solve for y. I hope that makes sense. Now let's take up the next example where we'll see how a quadratic function can be written in as inverse. Now we need to find inverse of a quadratic equation. Then we have to find it both graphically and algebraically, and then write domain and range for the function and its inverse. Now it is important to understand that for a quadratic function we need to write it in vertex form. So the first step here is to get it in vertex form, which could be done by completing squares. Once you have completed squares form, the vertex form, you can sketch easily, right? So we are given the function as y equals to 2x squared minus 4x minus 1. To complete the squares, we'll factor out 2. We get x squared minus 4 divided by 2 is 2x. Keep this one separate. Now we'll add and subtract half of the coefficient of x, which is 1 in this case. So we'll add 1 square and we'll also subtract 1 square. That makes first three terms as a perfect square, x minus 1 whole square. The fourth term is minus 1, open the bracket, so we get 2 times x minus 1 whole square. And here we have 2 times minus 1 as minus 2 and minus 1. So now the function can be written as 2 times x minus 1 whole square minus 3. Now to sketch this function, we know the vertex is at 1 minus 3. So 1, 2, 3, that's the vertex for us. Steps involved are 2. So if I move 1 unit up, I have to go 2 up. 1 unit up, right, you go 2 up. 1 unit, 2 up. So you kind of get a parabola, right? 1, 3, 5, 7 are the steps. Let me write down. Let me do this part again. So basically, we can have steps of 1, 3, 5, 7, and so on, multiplied by 2, right? So let's redo it. We do have the vertex as 1 and minus 3. That becomes the vertex. 1 unit up, 2 up for the first step. The second step is 2 times 3, 6. So 1 unit to the right, 6 up. 1, 2, 3, 4, 5, 6. Third step will be 10 up. So let's go up to only 6. Now second, you also know that this is a symmetric function about the axis. So we'll get these points, 1 unit left, 1, 2, 3, 4, 5, 6, right? So that is the parabola we're talking about. Okay. Now this parabola fails horizontal line test, and therefore its inverse will not be a function, right? So note. Right? As it fails horizontal line test, right? Okay. Now the second part is we sketch the function as such. Now what we need to do is to sketch the inverse graphically. To sketch graphically, we'll draw a line y equals to x, which is kind of like this. So this is y equals to x. We can reflect each point and then sketch the function. Here the point is at 1 minus 3. So it becomes, this point is 1 minus 3. So it becomes minus 3, 1, right? So that is how it gets reflected. So 1, 2, 3, and 1, minus 3, 1. So that is how that point is going to get reflected. So if you look at this arm, in that case we have a y-intercept at 0, minus 1. So you get a point here. Correct? So that is the second point. And then if you move further, we had a point right there, which is at minus 1. It is 1, 2, 3, 4, 5. In that case, that goes to 5 minus 1. So 1, 2, 3, 4, 5 minus 1. So this gives you 1/2 of the curve of the inverse function, which is kind of like this. Okay. For the other half, we'll follow the right arm of our parabola. So we are basically reflecting each point. Now this point here is 1 minus 2, which will be reflected at, this point is 2 minus 1, so it'll be minus 1, 2, right? So that is the point. And that is an invariant point. We can always take the invariant point and then sketch our parabola. Sketch the inverse of the function. So that reflects the inverse of our function. Perfect. So in this case, inverse has been sketched. I'm not writing as a function since it is not. It fails the vertical line test. Now let us see how to get the equation algebraically. To get algebraic equation, we'll swap x and y in the vertex form. So we can write this. This is y equals to 2 times x minus 1 whole square minus 1. I'll rewrite this as x equals to 2 times y minus 1 whole square minus 3. Bring 3 to this side, becomes x plus 3 equals to 2 times y minus 1 whole square. Now divide by 2. So we have x plus 3 divided by 2 equals to y minus 1 whole square. Correct? Now, to get the value of y, we'll square root. So let's do it on this side. So square root means we can write this as plus minus square root of x plus 3 over 2 equals to y minus 1. And now we can write y as 1 plus that. So we can write y as 1 plus minus square root of x plus 3 over 2. So that becomes the inverse of this function. So let me rewrite the inverse of the function right there. So f inverse is equal to 1 plus minus square root of x plus 3 divided by 2, which is shown here in green. Right? Now let's write down domain and range for both function and their inverse. That is this part. For f of x. Okay. So for domain, we know x belongs to real numbers. As far as the range is concerned, we know y is greater than or equal to minus 3, right? Where y also belongs to real numbers, but y is greater than or equal to minus 3. Now, the domain and range for the inverse will swap. So, domain and range for f inverse will be, as you can see here, the domain is on the right side of minus 3, correct? So, x belongs to real numbers where x is greater than or equal to minus 3. But as far as the range is concerned, it is all real numbers, right? Y belongs to real numbers. Does make sense to you? So you can again see that both domain and range, they flip, right? They swap. So that is how you can actually sketch graph of a function and its inverse, also calculate them algebraically and find domain range. Now let's take the last example, which is regarding the square root function. Now let us see how to find inverse of a square root function. We need to find inverse of f of x equals to square root of minus 2x plus 6 minus 1, graphically and algebraically. And we need to state domain and range for both. Now it is important to rewrite this function to understand its domain and range. We could write this as equal to, taking minus 2 common, x minus 3 minus 1. Now that gives you clearly the domain and range for the function. So the domain for the function here is x belongs to real numbers, where x is, since it is negative, it is reflected on y-axis from 3. So x is less than equal to 3. The range of this function will be y belongs to real numbers, where y is greater than equal to minus 1. Correct? So this is about the function. Now, when we do inverse, in that case, what will happen? In case of inverse function, domain and range will swap. So let me rewrite, or rather write domain range for inverse function first. So now our domain will become x belongs to real numbers, where x is greater than equal to minus 1. Do you see from here? It kind of swaps, and the range will be y belongs to real numbers, where y is less than equal to 3. You see that part? So domain and range swaps for function and inverse function, right? That is very critical to understand. And now let's do the algebra to find inverse. So let's find algebraic solution for f inverse of x. First step is to swap x and y. Let's go with this function. So we get x equals to square root of minus 2y plus 6 minus 1. Let's isolate y now. So we get x plus 1 equals to square root of minus 2y plus 6. Now we'll square both sides. Now as soon as you square both sides, you are making a mistake by making negative also as positive, right? And therefore, this is the time when you have to write your domain, which is that x should be greater than equal to minus 1 and y should be less than equal to 3. Now this is very critical. Now you should proceed forward, right? So you get from here x plus 1 whole square minus 6 equals to minus 2y, or y equals to, dividing by minus 2, we get minus half of x plus 1 whole square plus 3, right? So that becomes the inverse of the function. So let me rewrite inverse here. So inverse of this function is equal to, we get minus half x plus 1 whole square plus 3, where x is greater than equal to minus 1, right? You know why it is less than 3 since it is moving downwards. So you know y is less than equals to 3. That is clear from the equation. However, the critical part is to write x is less than minus 1, only then it is the correct inverse formula. Is that clear to you? Now I think you can pause the video, sketch the graph of both the function and its inverse. Now you can actually write down few values and then sketch it. So if x is 3, we get minus 1. So 1, 2, 3, minus 1. That's a good point. Now, if I have to get 2 here, then x could be 1, right? So at 1, it will be 2, right? So at 1, it is going to be 2. So we get a point there. So if you sketch, you get a graph kind of like this. Let's make a table of values to sketch this, because I didn't do minus 1. So we'll actually make a table of values. So we can write the values of x and then calculate minus 2 times x minus 3 minus 1. Is it okay? We'll begin with 3 since our domain is less than 3. So we'll begin with 3. If I substitute 3 here, we get minus 1. Right? And if I substitute, let us say, because we need the whole number, right? So if I substitute 1, in that case, 1 minus 3 is minus 2, times minus 2 is plus 2, square root is 2, 2 minus 1 is 1. Correct? If I substitute minus 1, and let's substitute a value which will give us a perfect square, which is 9 for us. Anyway, let's substitute minus 1. In that case, minus 1 times, this is minus 4. It gives us 8. Square root 8 is, we get, let's calculate. So we have square root of 8 minus 1. 1.82, right? Similarly, we can get other values. So basically, at 1, 1, we have 1, 1, which is a point, invariant point. So that is 1, 1. So the graph is kind of like this. Okay? So this is the graph of our function. To get the graph of the inverse function, we could draw a line y equals to x, which is right there, y equals to x. And we are going to reflect each point on this line. Reflecting the first point, which is at 3 minus 1, we get minus 1, 3, which is kind of here. And this is point which is invariant. And here we have a point which is kind of 1.2. So you could draw a graph which is kind of like this. Right? So that becomes a parabola going downwards from minus 1, 3. Do you see that? Minus 1, 3 going downwards. So that is how you would actually sketch the inverse of the given function. So I'd like you to actually take more points here and then sketch a nice and a better graph. But I hope you have understood the concept. We also see in this particular case that 1, 1 is invariant point. So let me write down. Since it is common to both, right? So that is the invariant point. As an exercise, you could actually find invariant points in the previous two examples. That could be a question for you. Let me write. So find invariant points for line and parabola in earlier examples, right? So I hope that makes sense. So I hope that summarizes and gives you good practice of how to find inverse functions using graph and algebra. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.